Hello friends, welcome back to another video. This time I'd like to explore degeneracy again on our pretty little example of an infinite potential well. Indeed, this is the only example we've discussed so far, but degeneracy is going to work even here if we extend the infinite well to 2 dimensions. So what we call degeneracy in quantum mechanics is if you perform the measurement and you obtain a value, you don't know what the state is, even though you've obtained a value. And this could be true if the measurement is not unique to that state. So what would this mean in our case? In our case, I'm saying that there's at least 2 configurations that will give the same energy when measured. There could be different ideas of measurement, of course. So I've drawn this potential well. It's in 2D and it's a square, all right? So it's not a circle. A circle would have a bit more difficult solutions. But what I'm saying is the potential is infinite everywhere outside of the square, and it's equal to 0 everywhere within the square. This point here will be the point 0, 0, and this point here will be the point pi, pi. The Schrödinger equation for any dimension is just minus nabla squared over 2m minus h bar squared nabla squared over 2m psi plus v psi equals e psi. And so in our case, nabla squared will be the partial derivative with respect to x squared and with respect to y squared. And we'll have psi, a function of x and y, of course. V is equal to 0, and so we end up with minus dx squared psi minus dy squared psi is equal to k squared psi, where k, just like last time, k squared is 2me over h bar squared. Cool. We could put everything to the right, or to the right. So we'll get this equals 0. And here you would use separation of variables. So you could say that psi of xy is, say, big X of x and big Y of y. And using this ansatz, you'd then get that a general psi can be written like a combination of these. I should write the boundary conditions, of course. Psi of 0, 0. Maybe I'll write it like this. Psi of 0 y is psi of pi y is equal to 0. And psi of x0 is psi of x pi is equal to 0, meaning it has to be 0 along the edges of the well so that it could get rid of the infinity of the potential. Okay, so psi of xy is x of x times y of y, and then you could just separate. We're just going to guess the basis of solutions, though, so as not to waste time on these differential equations. So let n and n prime be integers greater than 0, okay? So not equal to 0. And then psi n n prime of xy will be, I guess I'll write a n n prime, some constant, sine nx sine n prime y. Okay, I'm purposefully using n prime instead of something else, just sort of to make it clear that there's going to be a degeneracy, and because this n does correspond to like the principal quantum number that you might see in the hydrogen atom, so I don't want to lose that notion by using another letter. Okay, so does this satisfy first of all, it satisfies the boundary conditions, right? So boundary conditions are satisfied for all n prime, and n. Okay. It satisfies the equation, so called Schrodinger equation. We would get from the Schrodinger equation that n squared plus n prime squared plus k squared is equal, is equal to k squared, which would mean that 2me, or rather the e is h bar squared, n squared plus n prime squared over 2m. Right? Yes. So e depends on n and n prime. And as you can see, well, for example, e n prime n is equal to e n n prime. So there will be at least that degeneracy when switching n and n prime. I'm not sure if there are two pairs of natural integers whose natural numbers whose squares are whose sum of squares are equal. Maybe some number theorists know. Probably there isn't. Maybe there is. In any case, you could have energies that are going to be degenerate in this way as well in some other examples. But okay, so we have what the energy is. This is the quantized energy. So this follows from the Schrodinger equation, and let's check the normalization condition. So the normalization condition gives us this requirement. So it's delta n m, delta n prime m prime. And this gives us what? A n n prime squared is supposed to be equal to 2 over pi, because why? We know that we've had this like a billion times, that this integral sine n x sine mx is equal to pi half delta nm if you go from 0 to pi. So that's all I'm using. You have two of these. This is supposed to be then 2 over pi squared, so you could get rid of two of these. So that's what a n n prime is supposed to be. We just take the principal branch of this number, of the root of this number, because yeah, like I said, this initial state, the coefficient doesn't matter. As long as it's normalized, the phase factor doesn't matter. So we have psi n n prime of xy finally is equal to 2 over pi sine nx sine n prime y. Okay, so this will be our basis, and then a general psi of xy could be written as the sum over n and n prime of some constants c n n prime times psi n n prime. Okay, yeah, simple. And what's my point here? Well, my point is just with the energies. Actually, the wave functions don't really matter. So my point with the energies is that, so E11 would be h bar squared over 2m. And this is non-degenerate. It's the unique value. So if we measure E11, then state is 1,1, okay, afterwards. But E21 or E12 is equal to 1 plus 4, so that's 5 h bar squared over 2m. But also E21 is equal to 5 h bar squared over 2m. And so if we measure if we measure the energy and we get E12, right? Okay, let's call this epsilon 2, okay? And let's call this epsilon 1. Because, yeah, it's the quantity, right? So if you measure epsilon 1, you know that the state is 1, 1. But if you measure epsilon 2, then you know that either the state is either 1, 2 or 2, 1. But you're not sure. In fact, I wonder if the state is even collapsed to either of these by the measurement then. This is an interesting question. I'm sure there exists an answer to this question, but yeah, it's interesting. So imagine that psi, for example, was equal to, let's see, psi was 1 over square root 2, 1, 2, plus 2, 1. You would then have that h on psi. So, yeah, you would just get E2, right, epsilon 2, from both of these states. Because, yes, so this is an eigenvector of the Hamiltonian. In fact, any combination of these two would be an eigenvector of the Hamiltonian with eigenvalue E2. And so it's quite ridiculous. I don't know what would happen in a measurement. Would you be collapsed, or would you still have a superposition? I suppose you'd still have a superposition because nothing forces you to prefer one of these two. Okay, well, that's it. This was a shorter video to get the point across of what exactly degeneracy is. I hope you liked it. Bye-bye.